Okay, so this is a problem number 3 of our discussion problem. And this problem is asking about the predicting electrolysis reaction. So actually, this is the most important clue. And there are two types of electrochemical cell. One is galvanic cell, we also known as voltaic cell. And that one is essentially you are using chemical reaction to generate some kind of voltage device. So that's what's happening essentially inside of your battery. The second type is the other way around. You want to have the reaction to be happen when you apply in an external power supply, just like a battery. So using a battery, actually you can drive the reaction that is not spontaneous in otherwise, right? So that's what we call electrolytic cell. Okay, and so this is a case of electrolytic cell, and that's what we are talking about here. So I actually give a little pictures that I find it somewhere. So this is the concept. And so you apply to the negative and positive terminal using the battery. It looks like that. And because of that, the electrons are flowing here. And that's where a lot of electrons are here. And this is a negative terminal. And then that's where the reduction happens at cathode, right? In the electrolytic cell, and that's a negative terminal. And I probably many of you have sort of heard about this trick of red cat, right? Reduction is happening at the cathode. And the other way around is because the electron is depleting from here, so electron goes the other way. So there will be a positive terminal, and there will be an oxidation, and that will be an anode. And then you also probably heard about people are saying anode ox, right? So we are talking about cat versus ox, I guess. But it's cathode is for the reduction. And then let's see what's going on in this here. They say, okay, we are going to put some KBr, so K plus and the Br minus ionic species. And then you will have a copper 2 plus and the SO4 2 minus. So those are what's happening in here. So as you can imagine, these are the positive one that can be reduced by electron to get not copper, potassium. So the potassium ion, and so that's here the copper. Copper, I guess you need a 2 electron to make coppers, right? And whereas the other way, this one is going to be more like you need to be an oxidizing species. So this is let's talk about something that is a reduction, right? And there's a reduction. So in this side, so we can imagine that we are seeing copper plus competing with another potassium plus competing with copper 2 plus, right? Which one we want to get be reduced? That's what's happening in the cathode side, whereas the other side is bromine minus wants to be oxidized over SO4 2 minus. And then you also need to consider the last one, which is always there, and that is a compound called H2O. So H2O can be reduced or oxidized. So you might want to consider that for that case. Okay, so I want to consider the reduction of potassium plus, copper 2 plus, and the water. And that's what's happening in the red cat, right? Cathode, right? Cathode. The cathode reaction. So then you need to go to the standard electrode potentials and then find out the reduction of copper, reduction of potassium, and reduction of water. Okay, so this is a good one to see which one will be your favorite. And then do you remember this is a E reduction potential, and the higher you go up, this one wins. I mean this is a way that I will kind of remember. So there are different trend. Which one is winning this competition? The one at the top. The higher you go up, this is the one. So this is going to happen. So that's the reaction that will favor over the other two. So instead of potassium plus can be reduced, the copper 2 plus will be reduced into this, and that's a favored reaction. Okay. So and then okay, so this part is done, right? We took care of that. And so let's go to the other side, which is now the bromine side and the sulfate side and the water. In this case, I need to essentially consider the oxidation. So in reality, if you're looking at the bromine, for example, when they got oxidized, this one got stripped off, the electrons are gone, and then you would probably generate bromine 2, which is a liquid in the standard state. And to balance it out, you need 2 bromine, and then you need to have 2 2 electrons. So that's a reaction for oxidation, right? But however, you do not find this reaction on the table because standard electrode potential, as you can see, this is a reduction half reaction. So always look for something like bromine 2 liquid is reduced into the form of 2Br minus. And that's what you want to find out. And this is a value you'll find out from this table, which is a redox. And then you are going to use that value to recalculate the value that you want, which is oxidation. That is essentially negative of E reduction for the opposite reaction that is shown up here, right? So I want this too, but I want to use this one because that's the way that people always put this reduction potential. Okay, so then I need to look for something that is happening on this side. And so and at the bottom here is showing the one that bromine, water, and the sulfate, and how they are getting reduced from some previous form. Okay, and what we really interested in is we want to describe this one to the other way around, right? And so the value will be the other way around, right? Okay, and in this case for the oxidation, this one wins. So it's the opposite of the reduction. So that's how this one wins. So among all this is the one that is going to be the dominant reaction at the side. So therefore, so if I put this together in a more summarizing reaction in the cathode side, and you are going to have a reduction, right? Red cat, and the reduction happening in copper 2 plus is a favored into 2 electron and getting reduced into the solid metal. And the anode which is an oxidation. And then I need to looking at this, which is a reduction forms, and this reaction is turning to the other way around. So the way that I write is 2Br minus is going to be Br2 liquid with 2 electrons. That's an oxidation, right? This is a reduction. This is an oxidation. And then what's the value do I have here? Because it's a reduction, I can use the same value. And this is an oxidation. So I have to use a reverse value shown up here, which is a 1.09. So therefore, E cell here, if you want to write it, and that's a E reduction, E cell, and then the potential of oxidation, and that's a 0.34 minus 1.09 volts, and that's essentially minus 0.75 volts, right? So this is something that you need to also think about as being consistent with what we discussed in the previous problem. This is not spontaneous. So therefore, I want the reaction to be happening. So okay. So I forgot to mention to the net reaction. So let me write the net reaction. So combining these two, the net reaction is copper 2 plus 2 bromine minus is copper solid and the bromine to liquid. Okay, so this net reaction, this is not spontaneous. So it's only happened because we are enforcing it by using this, applying the extra power supply just as a battery to enforce this non-spontaneous reaction. That's what is called the electrolytic cell. So, copper sulfate, and then you can put potassium bromide. This is very kind of stable compound that probably has a less value, but now you are enforcing the batteries, and I guess you have to apply more than 0.75 volts. For example, you can apply 1.5 volts here, and then you have a big driving force to make the copper plating, and the other side is essentially this is where the anode is. Anode is having a bubbling where the bromine 2 liquid is happening on the surfaces, and in the cathode side, copper 2 is essentially depositing on the surfaces. Copper is that's what we call the copper electroplating. And you can make things on cathode surfaces, and you can make things shiny, just like a copper.